We may well call it black diamonds. Every basket is power and civilization. For coal is a portable climate, and it is the means of transporting itself whithersoever it is wanted.
Black diamonds were the material basis for 19th century technology. Ever since the early Industrial Revolution, coal had been used to raise steam for the engines in the mines, the factories, and of course on the railways. Engines that had transformed Britain into an industrial nation. But there was a more profound sense in which coal was to become important. From earliest times it had been burned in air as a fuel. Then it had been discovered that if coal was heated in the absence of air, it was decomposed. And this process of decomposition of coal was to lead to its exploitation in a new way as a raw material.
Most mortals on earth with smoke live in strife, and many a beauty is smothered alive. Smoke begot chimneys, chimneys beget smoke, soot, fires and filth, all prevented by coke.
That is an early attempt to sell a smokeless fuel, coke, the solid product obtained by heating coal in the absence of air. Since coke consists mainly of carbon, this process is often called the carbonization of coal. Near Blaydon-on-Tyne are some early Beehive coke ovens of a kind that date back to the early 19th century. They were built in 1860, and a year or two later, Professor Muspratt's Dictionary of Applied Chemistry gave this description.
The method of coking in ovens can hardly be excelled for the production of a hard, dense coke. Hence they're employed by several iron smelters. A common arrangement is a series of 4 ovens constructed in a line for the purpose of economizing the heat. Sometimes about 1,200 cubic feet of coal are charred in each at once. And the walls of this construction, including the fireproof facing, are about 2 feet thick.
Edward Lowes worked at these ovens until they were closed a few years ago.
Yes, well, it was all hand-filled by tubs, and there was 4 tubs to each oven. Each oven held about 6 ton of coal, and from that 6 ton of coal, they got about 4 ton of coke. The coke was cooled in each oven by big hoggers. After it was cooled, it was all hand drawn out with a big peel like a steel shovel, and was put on the benches. From the benches, it was hand filled into wagons by men with big coke rakes, and it was all hand filled. It was heated by a big flue at the back of each oven. It went right around all the ovens like a U-flue, and there was a back eye in each oven, and the heat came through there. Everything was left in the coke. That's how it was as good a coke as it is.
The only purpose of these ovens was to produce coke from coal. Everything else was burnt to provide heat for the process. One of the things that was lost was a gas, which we now know as coal gas. Back in the 18th century, this gas had been recognized and its properties examined.
I remember being much amused when a little boy by my uncle, George Dixon, filling an old tea kettle half full of coals and setting it in the fire. He joined a tobacco pipe to the spout with clay. After a certain time, he put the flame of a candle to the end of the pipe, and immediately a bright flame issued from it, where nothing was perceptible before. He had only made the discovery recently. This was probably the 3rd or 4th exhibition of illuminating rooms by gaslights.
Gaslighting didn't really catch on till the early years of the 19th century, when it owed much to the scientific experiments of William Murdoch and the intensive promotion campaign of Mr. Frederick Windsor. He saw himself as a practical man, rather than as a man of science.
I had a great contempt for theorists who could write but not practice, who could fill bladders from retorts but could not illuminate. Theorists whose delicate hands and noses would have shrunk with horror from numerous experiments in kitchens and washhouses. My own laborers complained of being suffocated and often refused to assist me, until I shamed them by stripping to perform what they thought too dirty work for them.
What can occasion such a ferment in every house, in every street, in every shop, in every garret about London? It is the Light and Heat Company. It is Mr. Windsor and his lecture, and his gas and his patent, and his shares. These famous shares which are to make the fortune of all who hold them, and probably will involve half England in ruin. That shining light which has lit up Pall Mall for this year past has all at once blazed up into a comet that bears everything along with it.
By 1810, people were talking of the triumph of gas lights.
And it shall come to pass that Mr. Windsor's patent gas will very soon eclipse the moon, and when that's done, put out the sun.
Lord Mayor's Day, 1815. Yesterday, this annual ceremony was celebrated with more than usual display. But the great and striking attraction was the renovated appearance of Guildhall. It would not be easy to conceive a more imposing spectacle than was presented when the whole company sat down to dinner. The profuse delicacies of the table, the waving feathers and sparkling jewels of the ladies, and the mild splendor of the gas. Altogether, they formed a magnificent combination, worthy the inauguration of the presiding citizen of the great city. Those who've been used only to the brilliancy of oil and candlelight can have no adequate idea of the effect of illumination by gas. It so completely penetrates the whole atmosphere that it appears as natural and pure as daylight.
By 1819, Frederick Ackham could report,
The number of gas lights in use in London amounts to upwards of 51,000, and the total length of mains to 288 miles. The gaslight illumination has also spread far and wide through the country. Establishments for the supply of the new lights are carried out at Birmingham, Kidderminster, Cheltenham, Bath, Bristol, Exeter, Manchester, Macclesfield, Chester, Leeds, and in many other towns and places in Great Britain.
The methods of gas production have naturally changed over the years, and coal gas is now largely replaced by natural gas from the North Sea. But in a few isolated places, such as Newton Stewart in southwest Scotland, something very like the original process still survives. Here the coal is heated in horizontal retorts by coke-fired furnaces. Samuel Clegg described the process in his famous treatise of 1841.
If coal is submitted to heat in closed vessels, all its immediate constituent parts may be collected. In order to apply this on a large scale, the coal is put into vessels called retorts. The retorts are fixed into a wall above a furnace. The heat of the furnace develops the gaseous and liquid products of the coal. The cycle begins when the charge of coke is drawn. But previous to drawing, the lid of the retort shall be loosed and a light applied to the issuing gas. This precaution is necessary to prevent explosion, or what the stokers call a rap. The charge of coke is withdrawn from the retorts and is directed through a wrought iron carriage to the furnace, which requires feeding. The forms of the retorts are various, but retorts of the kind called Ds allow of the coal being laid in thinner strata, and consequently are more evenly acted upon by the heat, an advantage under every circumstance. The most economical charge is 2 bushels of coal to each retort. This charge will fill the retort to the depth of about 5 inches. The dense vapours which pass from the retort rise through ascension pipes into the hydraulic main. The use of the main is to cut off communication between the retorts when one or more benches are charging or open.
Here, at the back of the retort house, the gas undergoes a series of purification procedures. After leaving the hydraulic main, it is cooled by passing through these condensers, long vertical pipes cooled by air. This deposits some tar. The rest of the tar is removed by washing the gas with water in these Livesey washers and in this scrubber. One noxious impurity left is hydrogen sulfide, the bad egg smell. This used to be removed by passing the gas through lime, or, in this case, iron oxide, in these large cast iron boxes. The flow of gas through all this equipment is kept up by an exhauster pump. This one is steam-driven. The flow of gas is measured in a meter and then passed into a gasometer to be stored. Now let's look at this process a little more carefully. Notice how some tar begins to separate in the hydraulic main. Much more is removed in the condensers. And it's finally eliminated from the gas in the washers and the scrubber. It's all collected in the tar well, where it settles underneath the water as a separate layer. The upper layer contains ammonia, and in the 19th century, this used to be extracted. Next, hydrogen sulfide is removed. The gas is metered and collected in the gasometer. All the while this process is taking place, there are vast quantities of tar accumulating. It's a dark, viscous, heavy, smelly, unpromising liquid, yet in it lay much of the future of modern industrial Europe.
Oil and ointment and wax and wine and the lovely colours called aniline. You can make anything from a cell to a star, if you only know how, from black coal. tar.
That was how Mr. Punch viewed this material. He was on the whole quite right. And the journey from tar to all these desirable products began with the age-old process of distillation. This is Scottish tar distillers at Falkirk, founded as James Ross and Company in 1845. The tar was heated to boiling point in great pot stills like these. Different fractions came off at different temperatures. They were condensed and collected separately. One early pioneer in coal tar distillation was a young man called Charles Mansfield.
The distillation of coal tar is a regular branch of trade. The operation is usually conducted in large iron retorts, capable of holding many hundred gallons. The first products that come over are ammonia and other permanent gases. As the temperature rises, water charged with various ammoniacal compounds passes over, accompanied by a fetid yellow or brown oil. The receiver is now usually changed, and the previous oily distillate set aside as light oil or crude naphtha. As distillation proceeds, heavy oil continues to run, free from water, very fetid, and of a yellow color, equal to about 30% of the tar. Distillation always begins to flag at this stage, and the operation is usually stopped. The black residue which remains in the retort and which solidifies into a hard vitreous mass on cooling is pitch.
One of the main products from this process of distillation was a substance called benzene. A white liquid with a characteristic smell that happens to be a very good solvent. As a matter of fact, it can be used for dry cleaning, and Mansfield discovered this and became the founder of the dry cleaning industry. But it's also very inflammable. It was from a benzene fire that Mansfield met his untimely death in 1855 at the age of 36. But far more important than its use as a dry cleaning fluid was the use that benzene was put to in the laboratory and later in industry as a synthetic intermediate. It could be employed for conversion into a whole range of other chemical compounds, the most important being nitrobenzene, a yellow, oily liquid with a smell of almonds. This nitration plant works on exactly the same principle as those of the 19th century. Benzene was treated with concentrated nitric and sulfuric acids in large iron vats. The benzene and the mixed acids are introduced into the vats and stirred mechanically. Temperature control is crucially important, and it has to be kept well below 65 degrees. Otherwise, the reaction may get out of hand. The next stage is the conversion of the nitrobenzene into aniline. This old plant was used for many years to produce aniline by the old process. Nitrobenzene was mixed with very dilute hydrochloric acid, and scrap iron was introduced through these hoppers. This mixture was stirred mechanically and then heated by steam. Aniline was obtained after a series of extraction and purification processes as another, almost colorless liquid. Both of these processes have been known for some time, but they assumed a dramatic new importance with the discovery that aniline had undreamt of synthetic possibilities. The great pioneer was A.W. Hoffman, at the Royal College of Chemistry in London.
Hoffman's power of directing research was most remarkable. With the aid of a few watch glasses, a glass rod, and a small gas flame, he would make a number of experiments, and from the information thus gained, tell his students how to proceed with their work. I well remember one day he came up and commenced examining a product of the nitration of phenol. He took a little of the substance in a watch glass and treated it with caustic alkali. At once he obtained a beautiful scarlet salt. Several of us were standing by at the time, and he looked up at us in his enthusiastic way and exclaimed, "Gentlemen, new bodies are floating in the air."
The student who remembered that story was William Henry Perkin, later to become famous in his own right.
As a young chemist, I was ambitious enough to wish to work on the subject of the artificial formation of natural organic compounds. I selected aniline. And treated its sulfate with potassium dichromate. In this instance, a black precipitate was obtained, and on examination, this precipitate was found to contain the coloring matter since so well known as aniline purple, or mauve. Very soon after the discovery of this coloring matter, I found that it had the properties of a dye, and that it resisted the action of light remarkably well.
Perkin's discovery was to revolutionize the dye industry. Not only was it a strong color, reminiscent of Tyrian purple, but it had a fair resistance to the action of light. This discovery of Perkin's was followed by many others, particularly in Germany. Soon there were hundreds of dyestuffs, all obtained from aniline and other related products. The variety seemed endless and resulted in a virtual explosion of brilliantly colored fabrics. We've traveled a long way in this program, from the first crude attempts at the carbonization of coal to the development of the coal tar dyestuffs, and they themselves were the beginning of a much longer story. But the important thing is that what began as attempts to find an outlet for this waste product of the carbonization industry, coal tar, was to lead eventually to the emergence of a great new science, the science of organic chemistry.
Say woof again! Say woof again!
I've got one that can see.
This is my kung fu, and it is strong.
See you later.